In this section, we're going to introduce hyperbolic functions. We're going to understand the definition and properties of hyperbolic functions, including some identities. We're going to compute the derivatives of these functions, and we're going to understand the relationship between these hyperbolic functions and trig functions, and understand where the names come from. So first, let's start with the definitions. We have hyperbolic sine and hyperbolic cosine. So this SINH is what we call hyperbolic sine, and we commonly just call this sinh. So sine h of x is sinh of x, and that is defined to be the function e to the x minus e to the negative x over 2. Whereas hyperbolic cosine which we're going to call cosh, is e to the x plus e to the negative x over 2. These definitions are very similar. The only difference is the negative in the sinh and the positive here in the cosh. So here is the only difference between the two. So right away, we're going to tackle the biggest misconception about these hyperbolic functions. And that is these definitions do not involve trig functions. Although we're clearly talking about something related to trig functions with sine and cosine, these two functions are defined with just a couple exponential functions. We're going to talk about the reasons why they're called hyperbolic sine and cosine, but when you have to do anything with these functions, you're going to go straight to the definition and use that. And we're just giving a nicer name to a more complex function, e to the x minus e to the negative x over 2, or plus that last term. So with that being said, we'll use those definitions in a little bit. Let's talk about the similarities between sine and cosine and sinh and cosh. So for sine and cosine, we have the nice property that sine of 0 is 0 and cosine of 0 is 1. And that's going to be shared in the properties of sinh and cosh. Sinh of 0 is 0 and cosh of 0 is 1. Then we get into more complex things, more useful things. We have that sine is one of our examples of an odd function. That means that it is symmetric over the origin, the x-axis and then the y-axis. And this means that sine of negative x is negative sine of x. And this is shared with the property with sinh. It is an odd function symmetric over the origin. Whereas cosine is an even function. That means if you plug in negative x, you just get the same function out, or cosine of x. And this is symmetric over the y-axis. And this is shared by cosh. This should be hyperbolic cosine here, as cosh is an even function. Then we're going to do derivatives, and we'll see why these derivatives are so useful too. The derivative of sine is cosine, and the derivative of cosine is negative sine, and they're almost just derivatives of each other. Sinh and cosh are actually nicer than that. The derivative of sinh is cosh, and the derivative of cosh is sinh. There's no negative involved. That's even nicer than the original functions. And then finally, we're going to think about the Pythagorean identity. Sine squared plus cosine squared equals 1. When we think about hyperbolic sine and hyperbolic cosine, there is a similar identity. This time it's going to be cosh squared of x minus sinh squared of x equals 1. So this is the reason why they're called hyperbolic sine and cosine, is because there's obviously a very strong relationship to those functions, but the functions themselves are only defined to be something with exponential functions. So now let's go through some of those properties, and we'll first start talking about the graph of the functions. So here are the graphs of sinh and cosh, and note that when we're writing these functions now, we're going to break it up as two fractions. Instead of everything over 2, we can have both parts over 2. This is going to help us kind of think about what happens to these functions with the end behavior, as that's what we're going to look at here. So let's think about as x goes to infinity for sinh of x, what happens to the function? That is, let's look at the limit of e to the x over 2 minus e to the negative x over 2 as x goes to infinity. Well, we have that. The first part, or actually we're just going to do the last part. The last part is going to go to 0 because e to the negative infinity is 0. Or we could think about e to the negative x as being 1 over e to the x. So that means that as x goes to infinity, sinh is going to approach the function e to the x over 2, which is the same thing as 1/2 e to the x. And that's what we're getting here. We have this dotted line here representing 1/2 e to the x. And we can see that as x gets bigger, our function approaches that line. It's kind of like an asymptote. It's kind of like a slant asymptote, except it's approaching a function. As x goes to negative infinity, we have that sinh is going to approach the other term. It's going to approach negative 1/2 e to the negative x. Because when we approach negative infinity, this first term will go to 0, and we'll be left with just the other term. So if we think about that dotted line, that function, that's this guy over here. It is a reflection over the x and the y-axis. And we have that our function sinh of x is something that's kind of approaching both those at the same time, one to the left and one to the right. And that is our function sinh of x. Cosh is done in a very similar way, except that as x goes to infinity, we have that cosh is going to approach e to the negative x over 2. That's the same thing. Sorry, e to the x over 2. And as x goes to negative infinity, cosh approaches e to the negative x over 2 without the negative. So those two functions we can see drawn here. And we have our function looks like a parabola. Note that it is not a parabola. And it is approaching kind of both those at the same time. So what's nice about this function cosh, we can think about the application of this function and why it might be useful, is that this shape that we have here, this parabola looking thing, even though it's not a parabola, is the shape that might that actually comes about if you have a wire or a line and you let it just sag naturally. If it kind of just sort of goes down to the ground, and how it's going to fall is going to be in that cosh hyperbolic cosine shape. And these functions do pop up in real life examples all over the place. But that is an example of where hyperbolic cosine comes from. All right, now let's talk about hyperbolic tangent. We're going to spend a lot less time on hyperbolic tangent, but we can know that it's going to be defined using the same idea as tangent being sine over cosine. We'll now do hyperbolic tangent, which we're going to call tanh. Tanh is going to be sinh over cosh. And when we do that, the over 2's cancel out, the 1/2's cancel out, and we're left with e to the x minus e to the negative x over e to the x plus e to the negative x. And we get this function out. It has some horizontal asymptotes. And on the worksheet this week, I ask you to investigate those by looking at the limits of that function. So one of the main reasons we talk about these hyperbolic trig functions is because the derivatives are so nice. The derivative of sinh is cosh, the derivative of cosh is sinh, and the derivative of tanh is very similar to what the derivative of tangent is, 1 over cosh squared instead of 1 over cosine squared. So let's think about how these derivatives come about. We have the derivative of sinh, when we use the definition, is going to be the derivative of e to the x minus e to the negative x over 2. So when you take that derivative, that's going to be 1/2 we can pull out in front of the derivative of e to the x minus the derivative of e to the negative x. The derivative of e to the x is just e to the x. And the derivative of e to the negative x is a very quick application of the chain rule. Inside function is negative x, outside function is e to the x. So we're going to take the derivative of the outside function, e to the power of something, leave the inside alone, and then multiply by the derivative of the inside. And altogether, that's going to give us 1/2 e to the x plus 1/2, or sorry, it should be 1/2 times all of this, plus e to the negative x, which we can write as e to the x plus e to the negative x over 2, and that is cosh. The derivative of cosh is very similar, so let's do that one real quick. The derivative of hyperbolic cosine will be e to the x plus e to the negative x over 2. When you do that derivative, you're going to have 1/2 e to the x minus e to the negative x, in a very similar way we did in the other problem, and that is exactly sinh. So when you're doing these derivatives, it's important to know that what we're really doing is just using those definitions and going through those exponential functions, and note that there's a nice kind of thing that comes out of it. We can just go back to those definitions each time. Let's do the derivative of tangent. That's going to be the derivative of the definition of tangent, not tangent, sorry. And that is going to be sinh over cosh, which is e to the x minus e to the negative x over e to the x plus e to the negative x. When you take the derivative, you have to use the quotient rule. So that's going to be the derivative of the top times the bottom plus the top times the derivative of the bottom over the bottom squared. Let's see how this comes about. So the derivative of e to the x minus e to the negative x is going to be e to the x plus e to the negative x. Just going to change that sign. We have e to the x plus e to the negative x here, plus e to the x minus e to the negative x, and the derivative here will be e to the x minus e to the negative x, all over e to the x plus e to the negative x squared. So before we go any further, note that I did make a small mistake with the quotient rule. You should have a minus sign here. And when we're doing this derivative, we now need to kind of bring it back into sinh and cosh. So each of those terms, e to the x plus or minus e to the negative x, we can write as 2 times sinh or cosh. So the ones in blue here, we can write as 2 times cosh. And the ones in green here, we can write as 2 times sinh. And we're going to use our Pythagorean identity. This is going to be 4 cosh squared x minus 4 sinh squared x all over 4 cosh squared x. The top is equal to just 4, that's the Pythagorean identity, over 4 cosh squared, and that is our 1 over cosh squared as promised. In the next video, we're going to look at some practice problems related to hyperbolic sine, cosine, and tangent. And again, remember that any problem that you are confronted with, you may have a nicer way of doing it with some kind of identity, but you can always just go back to the definitions of e to the x and e to the negative x. And we could have actually done that in this last problem here. We could have taken this and just done all of that foiling, and everything would have canceled out. We would have had a 1 over cosh squared when it was all said and done.